over here, assuming that the profile files have been created in the time it took us. Here, I can see detailed information for every thread and every node. If I click here, it shows me the time spent in the key code regions. And what are those? They are the do loops in the Z-solve, Y-solve, X-solve code regions, right? Here, on that thread of execution, I can right-click here and say, show me the source code. And it will go straight down to this do loop. Recall the same do loop here, where it spends all its time over here. I can look at this code and say, show me the, okay, this is interesting. I can left click or I can right click and look at the thread statistics table, or pick the call graph and other options. I can also take the same file and bring it down to my laptop, or click on Windows 3D visualization. And here, this is the triangle mesh, this is a bar plot. Let me just expand this a little and open up this window. And I can click and see from the FX10. I can use the scroll wheel or the plus or minus buttons to zoom in or zoom out, where I can see the MPI rank and thread. I can use this function slider this do body in this location in Z-solve or master or the Z-solve. This is the Y-solve, and the third function is the X-solve. Do you see these three functions? I can fly around and then check out these three peaks and see that there is a difference in the ranks. If I go down, you see here, this was taking 9.1 seconds on node 5 thread 1. Node 5 thread 2 takes just 6 seconds instead of 9. Then again it goes up to 9, and then it comes down to 6. So those patterns are very easily visible in the 3D display. I can also look at the topology, and Tau understands Fujitsu. If you had used a specific topology such as nodes equals 2 by 2 by 2, 8 nodes, then you would see a three-dimensional topology display for Fujitsu FJMPI's mappings, and you would be able to see exactly how much time was spent in each of those X, Y, and Z displays. So here's the bar plot. I can press the right button and translate, and first mouse button to rotate. Look at the color scale and see that this is the time spent from 0 to 10.3 seconds. And look at the full profile like that. Is this okay? Can everyone do this? Yes, Peter? on your local machine, right? Just do one little thing. Go to wget tau.uoregon.edu java.dmg. Just open it in the web browser and install this DMG file, tau.uoregon.edu java.dmg, restart paraprof, and it will all work. There's some problems with Apple's support for Java. This fixes all of those issues, even if you're running the latest El Capitan OS. Okay? So, for anyone on Macs, we recommend that you first install this Java DMG, then run paraprof. Although you can still do all the other things. So does this work for everyone? Any questions so far? It's just following along this readme.tau file where we first did the tau exec EBS, and now the more complicated version where we do this instrumentation. Now everything is getting instrumented. I repeat, everything is getting instrumented. The overhead will be higher. But Tau has a module to control the runtime of the application dynamically. It looks at the functions that are lightweight, that should not be instrumented. Functions like min, max, swap, and it disables the instrumentation in these calls at runtime by detecting that these are lightweight functions. So the program can start out a little slow, but then it can speed up and catch up, and you will still get the profiles in a reasonable amount of time. And you will be able to look at the display and see all these functions. Now you can say stack bars together or unstack them, and then each function has its own space. Like this. This is the do loop from the zsolve, and then this is the do loop with the ysolve, and here is the do loop with the xsolve. You can see the differences in each of those threads. Okay? And you can see which functions didn't execute at all on a given node. This is exactly the same as the 3D display, where each of those bars has been tilted up. Okay? I can look at this and bring the 3D visualizer and then, or look at the given, and then look at the bar plot and zoom in and compare the performance of these three functions. You see these three big functions, they are the ones that dominate. All the other things are small. So this shows you the shape of the profile. It shows you what is the distribution across all the functions. And it helps you identify these peaks in the profile in case you expect everyone to do the same thing and it's not doing the same thing. You can look at it and zoom in and examine in detail what's happening. Does anyone here have problems with the 3D display?
How do you
zoom in using the scroll wheel, or if you don't have that, with your fingers you can pinch, and if that does not work, use the old technique of just say plus and minus to zoom in. Shift plus and minus, and you'll be able to zoom in. No? Here? Here, there, see? Shift plus and shift. Minus, yeah, just minus. So plus, minus, and then first mouse button to rotate, second mouse button to translate and move the view. It'll get a little getting used to. It's an interesting tool. There are many things. Here's a render. If I click on the GL info, it'll show me that although it's coming from the FX10 system, it's actually using the OpenGL with hardware acceleration using the GPU on your laptop. This Intel HD graphics. Okay. And you see this button that's grayed out? And it says stereo. Now, if you had connected this to a 3D TV and you had those goggles on, you could connect this and turn on the stereo and see this in 3 dimensions. Okay, that makes for good demos if you. But here is the basic 3D visualizer. There are many different views that you can explore. You can look at these. You can see the metadata on every thread, see what each thread was doing. What was the operating system version? How was tau configured? If you want to configure it the same way, you can just follow these. Look at the name of the tau make file, when it was used. If you just have a profile file, it has a wealth of information. And even OpenMP information that's captured in the metadata. You can see all the tau environment variables. You can just pick from these if you would like to turn on some other options. For example, if you wanted to see the communication profile and you wanted to see the COM matrix display, you could do that. And if you wanted to see the 3D display, you could turn on the 3D options and navigate. Does anyone have any problems with looking at the value of any of these variables using the function and threads slider? If you want to change the fonts, you can again go to File and go to File, Preferences, and pick a different font like this and make it bold and apply. Change the size and apply. And you'll see that it takes effect. These functions are throttled. They are throttled because they are lightweight functions that take very little time and execute frequently. Okay? And you can see all of their names come in as throttled because it was not practical to instrument them at that level of detail. Yes, where it was... Oh, okay. If you want to just original state, you can just in paraprof, right? Or just restart it. Just or if you are or just close the windows that you don't like. And these are the two ones. There's a paraprof manager and then the visualizer over here. If you have too many windows open, you can just change that. Now you can also right-click and see the Add Thread to Comparison window. This is a very useful window where I can compare threads like this and pick any threads to compare. So I'm comparing these 3 threads and see the time spent on node 0, thread 0, node 0, thread 3, node 6, thread 0, and see the time spent in each of those do loops. Okay?
So, is that correct to understand that the first tau exec run shows the profiling, and now we are looking at the tracing?
No, this is not tracing. This is also profiling. It's just that this has a lot more instrumentation of the OpenMP regions, and we are collecting data from each thread of execution. We are instrumenting the source code. We are modifying the code by creating a copy of the code, adding hooks in the source code, then compiling it, and then creating the executable. The tau exec did not touch anything. It did not alter the source code. It did not alter the build system or the binary. It just took unmodified binaries and run it with just that tau exec-EBS to show you interesting code regions. So that's the key difference. That was sampling. In sampling, I'm just taking a lot of periodic interrupts to the program and collecting the data, looking at the program counter, where it is, correlating it to the source code, and suggesting that there is a good chance that the program spent its time in these areas based on the samples that were collected. It's not an exact science, it's just an estimate. With instrumentation, I am precisely measuring the effect of the execution of those functions and presenting that information here. This is not sampling. This is direct measurement. This is instrumentation because that's with tau exec-EBS. Exactly. Tau exec-EBS does the event-based sampling, which is precisely what you said, take the samples. Tau F77.sh actually adds the timer for start and stop at the beginning and ending of each function. If you wanted to use some other compiler option like opt-comp-inst, you could set the tau options that way and generate the profiles, and then you would not be using the source instrumenter, but using the compiler-based instrumentation for that. So, is anyone having problems in generating profiles, or are you able to? Yes, Peter? This view is by right-clicking here and then going down to add thread to the comparison window, and then picking another location, say here, and then also adding it to the comparison window. And then I can see the two and compare the performance. This can be very useful when this works also across different experiments. You can have multiple experiments that you can load up in Paraprof and compare one mean with another mean and look at the before and after results. Yeah. So you could, for example, if I had the first run and I said paraprof pack first.ppk, and then I ran it again, and then I said paraprof pack second.ppk, and I create two different ppk files like that, I could just say paraprof star.ppk and load both of them. Okay? In this case, it's the same thing, but imagine for a minute that these were two separate experiments. And then I could say, add thread to comparison window from this to this. You see that? I'm going to a different trial, and then I'm comparing from first PPK and second PPK to different things. So this can be useful. So my goal is not to show you a lot of slides, because I have a whole lot. My goal is for you to feel comfortable in the use of tau so that you might be able to apply it to your own program. And what I showed you is just scratching the surface of what all it can do. But there are easy to use tools, one which can just use sampling, the second that uses source instrumentation but throttles the unwanted routines at runtime, so you don't have to worry about it. In fact, if you wanted to make the instrumentation more compact, you could tell tau to generate a list for you for a selective instrumentation by saying, create a selective instrumentation file for me. And then it says, okay, well, my defaults are, if a function is called over 100,000 times, I look at the time spent per call. If it's less than 10 microseconds, I throttle it. And you can just pick the output file name. You can either change the parameter at runtime, and you could say, oh, why 10 microseconds? Even if it takes 25 microseconds, I don't care about it per call. So you could change it and you'd get a different list. You could change it to, instead of 100,000, just 10,000, and 250 and so on. And then you could just save it over here. So it says it's saved, and then you can re-instrument the code using this selective instrumentation file that it has created, saying these are the exclude list of functions. If you use this and re-instrument the code, it will work even faster. And if you wanted to say, I like that sampling, it showed me the source level information, I can turn it on by saying tau sampling equals 1 as an environment variable with any instrumented tau binary and get sampling along with source instrumentation if you want to go even deeper. Okay? But these are the two simple examples. By the way, does your 3D graphics work now with the Java? It worked, right? Okay. So here are some other views that I want to just quickly show you. I've in many cases pointed out exactly what you need to do to get this view, like launch paraprof, right-click on node 0, select thread statistics table, click on the column to sort, open the keys on the left, and so on. Do you feel reasonably comfortable in being able to use the event-based sampling? And the second part, just a show of hands, how many people were able to actually launch paraprof on a sample? Okay. Then you can set the tau makefile like this, copy it, and launch it. Here I'm seeing the metric, the green metric of time. This is the paraprof manager window. In case you are wondering what is the green and red, any metadata collected from a thread which matches exactly the same way on all threads of execution is shown in green. If a metadata does not match, such as the processor name, then it shows up in red, okay, and shows you the value on the metadata on node 0. Here, colors represent code regions. You can uncheck the stack bars together in options like this, and then you will get a view like that where you see each bar in its own space. Each color represents a function and it occupies its own space. You can see the exclusive time spent in the code region by just clicking on the node. You can click on the bar plot, move the function and thread sliders like this in the 3D visualizer, which you can get by going to the Windows 3D visualization. Right click here, show thread statistics table. You right click on a function, you can say show source code location and jump down over there like this, show source code by right clicking here. Then these functions are throttled. And then we also have support in tau for atomic events which are triggered spontaneously in the code. So there's the bracketed begin and end events, and there are other events such as, if you're tracking the memory usage, the memory footprint. The memory footprint can go up and go down. You can just sample it at different points in your code and then see the min-max values, or here's the energy usage in the code along a given calling path. 3D visualizer, we have the scatter plot. We have a scatter plot which shows you minima to maxima for 3 different functions. So you can see that this function, say MPI send, took between 10 seconds and 23 seconds. And then it takes the 3 functions that have the most standard deviation and the 4th one as the color, and then it just selects those to show you the variation, the extent of variation. And then you can pick different ones if you like, and scatter plot will show you the ball represents each thread. It has a unique value for the 3 functions and the color value. So it just puts the ranks all on the same view. So you can see that there is a inverse correlation between MPI send and MPI barrier in that application. You see this wall going diagonally. So you can see the shape of the profile. Here is a torus view, the topology view. And you can right click on the metadata. And here I have chosen, while submitting the PJ sub, with node equals 6 by 6 by 6 in the case of Fujitsu. And when I run this, it shows me the Fujitsu size is 6 by 6 by 6 array of nodes and the coordinates of those nodes for a given rank. So you can see what happens here. And then you can see the 3D topology display. Here, this is code that I just ran. You can see the home S11505 with the node equals 2 by 2 by 2, and I ran it with tau exec-EBS. And look at the topology plot for Fujitsu, and it shows me the coordinates and dimensions and where each node is located for a given function. Like this is a summary matmul sub which goes from 1.5 to 1.8, and for this function it shows me the 2 by 2 by 2 array and which one is hot and which one is cold, which nodes. So you can see the physical topology of your machine as given by the node parameter to FJ MPI, and it just pulls it out with no changes to your code. Just tau exec-EBS will provide that. And here is the node view. You can see the comparison view. We have a performance database where you can add applications, experiments, trials. This is the file preferences view. We can also collect functions together. If you saw xsolve, ysolve, and zsolve, and you said, I want to just group these together and not see everything else, then you can do that. For instance, if I said paraprof, and I look at the profile, and there's a lot of functions here, and I say, I want to focus on these do loops. And I could just say, launch the group changer window. Okay? And here, I can create new groups dynamically, and I can pick the loops that I want and change them to belong to one or the other functions. So I could say, here's my do group. This is a new group, and I click on, say, a do loop over here, and all of these barriers. And it says its current group is OpenMP, but I can click on it and say, here's the do group. And then I can look at the group legend, and there it comes up as do group. I could say, just show this group. Then here are all the functions. So I can zoom in to a piece of code or the names of functions by aggregating them in a new group and reason about them. This can be very handy if you want to just focus on a few functions and not worry about the whole profile. This is a derived metric panel where I can create different metrics such as floating point instructions divided by time to create flops. I can even have a set of instructions such as if I have a PAPI profile and I say hit ratio, miss ratio, and I say A divided by B and 1 minus A divided by B, and then the metric of hit or miss ratios can show up in your these metrics window. You can sort a metric by a different way. So you could say, I'm using the derived metric of flops, but I want to not show the functions that have the most flops. I'm interested in seeing the list sorted by the exclusive time spent in the node. So the functions that are at the top take the most time, and so I can see the flops for the functions that matter the most to me. So I can see all of these got like 3 gigaflops, but these ones didn't. So that's as far as tau is concerned. I do not have time to cover Perf Explorer. I encourage you to look at this. It allows you to do a lot of interesting analysis with, there are also some canned examples that you can try. And it allows you to do k-means clustering. It can allow you to look at how events are related to each other. It allows you to pick multiple experiments and show them from the database. You can store the data in a database. You can expand it. You can see the charts and create charts for different runs. And relative efficiency, you can see this is the ideal line. This is where all the different experiments lie. Within that, you can see relative speed-up curves. You can see total breakdown at different core counts. You can see evaluate the scalability of the code. There are many interesting charts that it can produce, even do regression testing. So you can store the data every night in the database and then pull it out and connect to the database and plot those charts. At this point, I would like to just thank our sponsors, the U.S. Department of Energy, the Office of Science, Pacific Northwest National Labs, Lawrence Berkeley, Oak Ridge, the NNSA, Tri-Labs, Livermore, Sandia, Los Alamos, the Department of Defense in the U.S., the MOD Office, the NSF, National Science Foundation, Software Development for Cyber Infrastructure, ACI, and our partners at Jülich Supercomputing Center, Argonne National Labs, TU Dresden, Paratools Inc. for their help with the Tau project. And you can download the Tau distribution from this URL. We also create live DVDs and OVA images that you can use for a virtual instance in VirtualBox, and you can download it from HPC Linux as the VI-HPS live DVD that was mentioned earlier by my colleagues here. Any questions before we continue for lunch? We have 1 minute, one question.